4 earthquakes, 4 days, 4 completely different corners of the planet, magnitude 6 or above, each one: Antarctica, the middle of the Atlantic Ocean, Tonga, Samoa. On paper, these regions share nothing. Different plates, different fault systems, different geological histories. They should not be doing the same thing at the same time, and yet here we are. Now here is the part that stops being a coincidence and starts being a question nobody in mainstream science wants to answer out loud. Every single one of these earthquakes struck while a powerful solar storm was battering our magnetosphere. A new study out of Kyoto University just proposed the mechanism that connects those two facts, and once you understand it, you cannot see what's happening right now the same way ever again. Stay with me, because tonight's investigation changes everything. If this has you hooked and you genuinely enjoy what I do here, feel free to subscribe to the Skylab, because this story is not finished and we are watching it in real time. The next solar event is already inbound, the clock is running. Drop a comment and tell me honestly, if the sun has been quietly influencing when earthquakes strike, and we have only just figured that out, what else are we measuring wrong? I genuinely want to know what you think. Now, let's get into it. Part 1. The 72-hour pattern that shouldn't exist. Something happened last week that nobody is talking about loudly enough. 3 separate regions of the Earth, sitting on completely different tectonic systems, with completely different geological histories, all started shaking within 72 hours of each other. Not small tremors, not background noise, major earthquakes. The kind that get logged, studied, and flagged by every seismic monitoring network on the planet. The kind that, when they happen once, get noted. When they happen 5 times in 72 hours across unrelated fault systems, they start demanding a different kind of attention entirely. March 20th, Antarctica, the South Shetland Islands. A magnitude 6.6 earthquake tears through the crust at just 4.9 kilometers below the surface. That is almost embarrassingly shallow. That is not a deep, slow grind of tectonic plates far underground, where temperatures and pressures turn rock into something closer to plastic. That is the Earth's skin splitting open. The kind of rupture that happens close enough to the surface that everything above it shakes violently, that the seafloor deforms visibly, that pressure waves punch upward through kilometers of water and rock with almost nothing to slow them down. Then cut to March 21st. The Mid-Atlantic Ridge, another magnitude 6.6. Now, this one matters in a way that takes a second to appreciate. The Mid-Atlantic Ridge is a divergent boundary. Plates are pulling apart there, not colliding. The seafloor spreads. New crust is created continuously as magma wells up from below, cools, and solidifies into fresh ocean floor. Major earthquakes on divergent boundaries are rare. The forces involved usually don't accumulate enough stress to produce something at that magnitude. The rock is young, relatively warm, and being constantly refreshed. It does not tend to store the kind of elastic strain energy that produces large ruptures. And yet, there it was, logged, confirmed, sitting in the data like something that had wandered in from the wrong geological neighborhood. Then, March 22nd, Tonga and Samoa. A magnitude 6.3, followed by a magnitude 6.2, followed by another magnitude 6.2. 3 significant earthquakes inside roughly 24 hours, clustered in one of the most seismically active arcs on the planet. Yes, but the timing compressed in a way that catches your attention, even in a region where earthquakes are relatively routine. 3 events of that size in that window is not unheard of in the Tongan arc, but it is not background noise either. It is a cluster inside a cluster, an anomaly within an already anomalous week. 3 different tectonic systems, 3 different corners of the planet, all firing within 72 hours of each other, and here is where it gets uncomfortable. If you pull up a globe and look at where the South Shetland Islands sit, then look at where the Pacific sits in relation to it, you start to notice something about the geometry. These events are not just distant from each other. Some of them sit near antipodal positions, meaning nearly opposite sides of the same sphere, the same Earth, reacting at almost the same moment. When you try to draw a conventional seismological explanation for that, one involving internal stress transfer through the crust or dynamic triggering from a preceding earthquake, the geometry simply does not cooperate. The distances are too large, the fault systems are too disconnected, the standard toolkit does not reach. Now, individual magnitude 6 plus earthquakes are not impossible. The planet produces roughly 120 of them every year. That breaks down to about 2 or 3 per week if you spread them evenly. What you're not supposed to get is this kind of distribution. Different fault systems, different plate boundaries, different geological contexts, all activated in a tight temporal window. The probability of that happening by pure random chance decreases meaningfully as the number of unrelated systems involved increases. 3 is not a magic threshold, but 3, distributed the way these were, distributed across hemispheres and geological categories, starts nudging the needle away from comfortable randomness. The question that keeps surfacing when you look at this pattern is deceptively simple. Why are these regions behaving like they are connected? Because here is the other detail that refuses to stay in the background. During those exact same 72 hours, from March 20th through March 22nd, the Earth's magnetosphere was under assault from a G3 geomagnetic storm, strong category, solar wind hitting speeds around 700 kilometers per second, the interplanetary magnetic field flipping southward at negative 28 nanoteslas, which is the configuration that allows maximum energy transfer from the solar wind into Earth's magnetic system. Auroras were visible from mid-latitude locations that almost never see them, places where the night sky does not typically perform that particular light show, places where people stepped outside, looked up, and reached for their phones because nobody was going to believe them otherwise. So you have the solar storm arriving, you have the earthquakes following, and you have a new study out of Kyoto University that may have just provided the physical mechanism that connects those two things, not speculatively, not through numerology or pattern matching in the dark, through applied physics, through a model of how electrical fields generated in the upper atmosphere by solar forcing can propagate downward into the crust and apply measurable pressure to fault zones that are already sitting at the edge of failure. The easy answer is coincidence. Seismic events cluster sometimes. Solar storms happen regularly during solar maximum. 2 things happening at once does not mean one caused the other. That is a critical point, and anyone telling you otherwise without qualifications is selling you something you should probably leave on the shelf. But here is the honest tension. Dismissing the timing as pure coincidence requires you to ignore the geometry, ignore the unusual distribution across fault types, ignore the specific magnitude clustering, and ignore the timing overlap with a well-documented space weather event. That is a lot of ignoring. The question is not whether we can ignore it. The question is whether we should. And a growing body of research suggests we should not. What happened in those 72 hours, viewed against the backdrop of emerging solar seismic research, looks less like noise and more like a signal. A signal we are only now beginning to have the instruments and the theoretical framework to read. Something in the pattern of the last 72 hours does not look like standard background seismic noise, and a new piece of research may have just given us a reason to stop treating that as a comfortable thought. Part 2. The numbers don't look normal. Let's stay with the data for a moment, because this is where the pattern stops feeling abstract and starts feeling like something sitting directly in front of you on a table, refusing to be moved. In the 7 days surrounding these events, the United States Geological Survey logged 115 earthquakes at magnitude 4.5 or greater. 115 in 1 week. The typical baseline for a week like this sits somewhere between 20 and 23 events at that threshold. What we observed was approximately 5 times higher than normal. 5 times. That is not a rounding error. That is not seasonal variation in how sensitive the monitoring networks are. That is not an artifact of improved instrumentation from a single upgraded station somewhere. That is a number that demands an explanation, even if the explanation turns out to be mundane, and the explanation, when you go looking for it, does not immediately resolve into something mundane. Now, the honest thing to do here is acknowledge that seismology is complicated. Not every week is created equal. Some regions go through active phases driven by local geological processes that have nothing to do with anything outside the Earth. Aftershock sequences can inflate counts dramatically after a major event, sometimes producing dozens or hundreds of smaller earthquakes in the days following a significant rupture. Data collection has improved significantly over the decades, which means we catch more events now than we did 30 years ago. A 4.5 that would have been missed by sparse networks in 1995 gets logged cleanly today. All of that is true. None of it fully accounts for what showed up in the numbers last week, because the events were not aftershock clusters from a single preceding major earthquake. They were distributed. They were across different systems. They did not trace back to a single initiating rupture. The concept you need here is the Poisson distribution. This sounds intimidating, but the core idea is simple enough to explain with a handful of coins. When events are truly random and independent, they should scatter roughly evenly across time. Some weeks will have more, some fewer, but the distribution should look spread out when you graph it. What you're not supposed to get is a dense cluster of significant events compressed into a narrow window across unrelated fault systems. That is the statistical equivalent of flipping a coin and getting heads 12 times in a row. It can happen. The mathematics allow it. But when it does, you at least ask whether the coin is fair before you move on. There is also a cognitive trap worth naming directly, because intellectual honesty requires it. Humans are pattern recognition machines. We're so good at finding patterns that we find them even when they are not there. Psychologists call this apophenia, the tendency to perceive meaningful connections between unrelated things. It is why people see faces in clouds and conspiracy and coincidence. It is why someone can look at a random scatter of stars and see a bear or a hunter or a dipper with a handle. And it is a genuine risk when you're staring at seismic data during a geomagnetic storm, already primed by headlines to expect something unusual. But here is the counterpoint, and it matters. Acknowledging the risk of apophenia does not mean every pattern is imaginary. The scientific method exists precisely because human intuition needs checking, because we need a process that filters out the faces in the clouds from the things that are actually there. And when you check the intuition against the numbers in this case, the numbers do not immediately clear. 115 events at magnitude 4.5 or above in 7 days, distributed across Pacific Ring of Fire systems, mid-ocean ridges and polar regions simultaneously, is not a pattern that dissolves under scrutiny. It gets more interesting the more carefully you look at it. Historical records do show similar spikes. There have been weeks in the past where seismic activity ran elevated above baseline, sometimes significantly. Geophysics is not a perfectly steady drumbeat. But what makes this cluster different is not just the count, it is the distribution. Previous spikes in the historical record often centered on a single region, experiencing a major event followed by its aftershock sequence, inflating the regional count dramatically while other parts of the world stayed quiet. What happened last week spread across geologically unrelated systems on multiple continents and ocean floors without a clear single initiating event that could explain the others as downstream consequences. The numbers do not look normal, and what makes this genuinely worth your attention is not just how many earthquakes occurred in that window, it is where they happened and what the map looks like when you plot them all at once. Because when you do that, the geometry becomes very difficult to explain away with standard models, and geometry, it turns out, is the part of this story that carries the most uncomfortable implications. Part 3. Opposite sides, same moment. Pull up a globe in your mind. Put your finger on the South Shetland Islands, sitting at the tip of the Antarctic Peninsula, curling out into the Southern Ocean toward the Drake Passage. Now push that finger straight through the centre of the Earth and see where it comes out the other side. You land somewhere in the Northern Pacific. Now look at where the Tonga-Samoa cluster sits. Now look at where the Mid-Atlantic Ridge rupture occurred. These points are not identical antipodal matches in every case, but the distribution across the planet's surface traces something that looks less like random scatter and more like global coverage. Multiple fault systems, multiple hemispheres, multiple tectonic contexts, all activated inside the same brief window of time. Antipodal geometry matters in this context because of what it implies physically. If two seismically unrelated regions on opposite sides of the planet activate nearly simultaneously, the obvious internal explanation, which is stress transfer through the crust, runs into a fundamental problem that physics will not let you argue around. Seismic waves travel through the Earth at speeds between 5 and 13 kilometers per second, depending on the wave type and the material they are moving through. P waves, the compressional waves, punch through the mantle relatively fast and can traverse the entire planet in around 20 minutes. S waves travel slower and do not penetrate the liquid outer core at all, which creates a shadow zone on the far side of the Earth from any given quake. The mechanics of how one earthquake could directly trigger another thousands of kilometers away through completely different tectonic systems with no intervening fault connectivity do not hold up under standard models. The energy attenuates too fast. The fault systems do not share stress fields. The geometry of plate boundaries simply does not connect them. Space Weather News publicly flagged this distribution pattern as it was unfolding, and the observation resonated because it articulated something that was already nagging at anyone watching the data carefully. Earthquakes can trigger other earthquakes through dynamic stress triggering, where passing seismic waves temporarily destabilize nearby faults by changing the stress state long enough for a critically loaded system to fail. This is a real mechanism. It has been documented. But the key word there is nearby. The documented cases of distant triggering involve faults along the same fault system or within regional stress fields, not antipodal points separated by the entire diameter of the planet and sitting on unrelated tectonic boundaries. Think about striking a bell. When you hit it, the entire bell vibrates. Every part of the metal responds to the impulse simultaneously, or nearly so. Not because each part triggered the next part in sequence through some chain of local interactions, but because the force was applied to the system as a whole, and the whole system responded. The vibration is global because the impulse was global. The question the antipodal distribution raises is whether something struck the Earth like a bell last week. Not a point force from inside, originating at one fault and radiating outward. A global force from outside, applied to the entire surface simultaneously, leaving the response pattern determined by which parts of the system were already primed to answer. No known mechanism in traditional seismology accounts for this. There is no accepted model where an internal tectonic process creates simultaneous activation of unrelated fault systems on opposite hemispheres within 72 hours. The internal geology simply does not work that way. Stress accumulates locally, over years or decades, along specific fault zones defined by plate boundary geometry. It does not broadcast globally, does not skip across ocean basins, does not reach through the mantle to tap a fault system on the other side of the world. The internal forces are real and enormous, but they are local by nature. So the question that follows is almost uncomfortable in its logic. If the trigger is not inside the Earth, and internal mechanisms cannot account for the distribution, where is it? And this brings us back, directly and unavoidably, to the timing of that geomagnetic storm. Because an external force, one acting on the planet as a whole simultaneously, would not care about fault connectivity. It would not distinguish between the Antarctic margin and the Tongan arc because it would not be travelling through the crust at all. It would apply pressure everywhere at once, through a different medium entirely, and which faults responded would depend entirely on which ones were already closest to their breaking point. The pattern on the map does not prove that is what happened, but it is exactly the pattern you would expect if something from outside was doing the pushing, and the fact that we now have a proposed physical mechanism for how that pushing could work makes the pattern significantly harder to dismiss than it was even 6 months ago. Part 4. The depth clue everyone missed. Here is the detail that most coverage glossed over completely, and it might be the most important clue in the entire pattern. The South Shetland earthquake on March 20th struck at 4.9 kilometers depth. The Tonga cluster events on March 22nd were occurring at approximately 10 kilometers depth. These are extraordinarily shallow earthquakes, not just shallow by the casual definition, but shallow in a way that carries specific physical implications for how they respond to external forcing, and specifically for how they would respond to the kind of electrostatic mechanism the Kyoto University model proposes. To understand why that matters, you need a quick sense of the depth spectrum. Earthquakes span a remarkable range. Deep focus earthquakes occur between 300 and 700 kilometers below the surface, originating in the subducting slab material where rock behavior changes under extreme pressure and temperature, becoming capable of sudden brittle failure even at depths where you would expect ductile flow. Intermediate earthquakes happen between 70 and 300 kilometers. Shallow earthquakes, classified as anything above 70 kilometers, are the most common and typically the most destructive because the rupture is close to the surface where human infrastructure sits and where the energy has less distance to travel before it arrives. But within shallow earthquakes, there is still enormous variation in what that depth means physically. 10 kilometers is very different from 60 kilometers, and 4.9 kilometers is almost at the surface. That is less than 5 kilometers of rock between the rupture and open air. You could drive that distance on a highway in about 3 minutes. Why does this matter for the solar storm connection? Because the shallowest zones of the crust are the most sensitive to external pressure changes. The rock there is cooler, more brittle, more fractured, and often saturated with fluids that move through the fracture network under pressure. These fault zones sit at what geophysicists call critically stressed conditions, meaning they are already near their failure threshold. The forces keeping them locked are not overwhelming the forces trying to slide them apart by a large margin. They are balanced at a razor's edge. They do not need a large nudge to rupture. They need just enough additional stress to cross the line, whatever form that additional stress takes, whether it comes from the slow creep of tectonic loading or from something arriving from a completely different direction. Think of a door that is almost swinging open on its own, a door that has been pushed to within a millimetre of its latch releasing. The spring is wound, the mechanism is primed. You do not need to kick it, you need to breathe on it, and the breath in this case might be coming from 93 million miles away. The Kyoto University model, which we will spend more time with in the next section, specifically predicts that whatever solar-driven electrical mechanism is proposed would have its strongest effect in the shallow, fractured zones of the crust, not in the deep, hot, ductile mantle where electrons do not behave the same way, not in the intermediate zones where pressure is enormous and the rock has been transformed into something that does not fracture the way surface rock does, but in the shallow, cold, fractured, fluid-saturated zones where electrical fields can penetrate, where the microscale geometry of cracked rock and water-filled voids creates the conditions necessary for charge amplification. The mechanism does not need to provide enormous energy. It needs to provide just enough to push a critically stressed system over threshold. Both the South Shetland region and the Tonga Arc have additional geological context that makes shallow sensitivity particularly plausible and worth noting explicitly. Deception Island, sitting within the South Shetland system, is an active volcanic caldera, one of the few places on Earth where ships can actually sail into the interior of a volcano through a breach in the caldera wall. The heat, the fluid movement, the ongoing volcanic degassing, all of these keep the shallow crust in a state of constant pressure fluctuation and chemical alteration that maintains it perpetually close to failure thresholds. The Tonga Arc is one of the most volcanically and seismically active chains on the entire planet, home to the Hunga Tonga eruption of January 2022, the most powerful volcanic explosion recorded in the modern instrumental era. Both regions are geologically alive in ways that keep their shallow crusts in a near constant state of elevated stress and fluid movement. These are not stable, cold, dead fault zones buried under ancient, undisturbed rock that would require enormous external forcing to rupture. These are systems already operating near their limits, maintained there by continuous internal geological activity. And all of the earthquakes in this 72-hour cluster that drew the most attention were shallow. Not moderately shallow, extremely shallow. The shallowest faults would be the first ones to respond to any external pressure signal, however small. And the pattern of which faults responded looks exactly like the pattern you would predict if you were specifically targeting the faults most sensitive to electrostatic forcing from above. Part 5. The solar storm that arrived right on cue. Let's talk about what was happening in space during those same 72 hours, because the timing here is either one of the most remarkable coincidences in recent memory, or something that genuinely needs to be taken seriously by anyone who looks at it with an open mind and a willingness to follow the data wherever it leads. On March 18th, the Sun launched a coronal mass ejection. A large plasma cloud carrying billions of tons of magnetized solar material punched outward through the solar system at speeds that would get it to Earth in roughly 2 days. This is not an unusual event during solar maximum. The Sun launches CMEs regularly, sometimes multiple per day during active periods. What determines whether a given CME is significant for Earth is not just its size or speed, but its magnetic field orientation, specifically whether the field embedded in the plasma cloud is pointing southward when it arrives, which determines how efficiently it couples to Earth's magnetic field. On March 20th, the leading edge of that cloud arrived. The magnetosphere compressed. Geomagnetic indices started climbing within hours. By March 21st, the storm had reached G3 classification, which is the strong tier on NOAA's 5-level scale, 2 steps below the most extreme category. The KP index, which measures global geomagnetic disturbance on a scale from 0 to 9, hit 7. Solar wind velocities were clocking around 700 km per second, which is roughly twice the typical background speed of 300 to 400 km per second that the solar wind maintains during quieter periods. The interplanetary magnetic field's southward component, designated BZ, dropped to negative 28 nanoteslas. That southward orientation is the critical factor. When BIS turns south, it aligns anti-parallel to Earth's northward field at the magnetopause, which allows magnetic reconnection to occur, essentially allowing the solar wind's magnetic field to merge with Earth's and pump energy directly into the magnetosphere. A strongly negative BZ is essentially the solar storm unlocking the door and walking in uninvited. Auroras appeared across parts of Europe, North America, and even lower latitude locations that rarely see them. People in places like Germany, Poland, the northern United States, and parts of the UK stepped outside and watched green and red curtains ripple across skies that normally show nothing more dramatic than clouds. The event was widely photographed and shared, which is how geomagnetic storms make the news these days, not through official announcements, but through thousands of people simultaneously posting photos of colours in the sky that should not be there. The G2 conditions that followed the peak meant the storm's effects continued for more than 24 hours after the initial impact, maintaining elevated geomagnetic disturbance well into March 22nd. Now overlay that timeline on the earthquake sequence with precision. The South Shetland magnitude 6.6 struck on March 20th, which is the same day the CME arrived and geomagnetic disturbance began before the storm peaked. The Mid-Atlantic Ridge magnitude 6.6 struck on March 21st, which was during the storm's peak activity when KP was at its highest. The Tonga-Samoa cluster of 3 significant earthquakes struck on March 22nd, which was after the peak, but while G2 conditions still persisted and the magnetosphere remained disturbed. Before, during, after. 3 phases of the storm, 3 phases of the earthquake cluster. The events bracket the storm's life cycle in a way that is almost choreographic, almost too clean to be accidental, almost, but not quite, which is exactly where the scientific tension lives. Now here is where existing research enters the picture and begins to make the timing feel less like coincidence and more like a documented pattern. Published work in peer-reviewed journals has flagged correlations between geomagnetic storm activity and earthquake occurrence across multiple independent datasets, with the earthquakes often appearing not at the storm's peak, but with a lag of roughly 24 hours afterward. The Tonga cluster, arriving on March 22nd, sits squarely in that lag window relative to the March 21st peak. Not approximately, precisely. If you had read the published correlation studies before the week began and used them to predict when earthquakes would most likely appear relative to the storm timeline, you would have pointed at March 22nd. Is this proof? No. That word needs to be said clearly and without embarrassment. Correlation is not causation, and saying so is not a cop-out. It is basic scientific honesty that protects you from drawing conclusions the data does not yet support. Geomagnetic storms are common enough, and seismic events are common enough, that overlaps will occur by chance with some regularity, even without any physical connection. The question is whether the overlap in this specific case, with this specific geometry, at this specific magnitude distribution, in this specific lag window, rises above what chance predicts. And that question has a potentially uncomfortable answer, waiting in a paper published out of Kyoto University just weeks before these events unfolded. Part 6. The Kyoto University Mechanism. In February 2026, researchers Mizuno, Kao and Umeno at Kyoto University published work proposing something that the seismology and space weather communities had been circling for years without ever fully committing to in a single coherent framework. They proposed a complete physical mechanism for how changes in the ionosphere, driven by solar activity, could translate into measurable stress changes inside the Earth's crust. Not a statistical correlation presented without explanation. Not a hand-waving argument about energy fields and planetary connections. A mechanism, step by step, with physics. The core of the idea is electrostatic coupling. This is not mysticism, and it is not New Age speculation about cosmic vibrations. This is applied physics grounded in well-established principles of electrostatics and atmospheric electricity. And the way to understand it starts with a structure that already exists in classical atmospheric science and has been studied for over a century: the global electric circuit. The Earth's surface carries a net negative charge. The ionosphere, the electrically active layer of the upper atmosphere sitting roughly 60 to 1,000 kilometers above you right now, carries a net positive charge. Between them sits the atmosphere, acting as a weakly conductive medium that allows a slow, continuous flow of current. The result is a natural capacitor. Two charge plates separated by an insulator, maintaining a voltage difference of roughly 300,000 volts between the ground and the ionosphere under normal quiet conditions. This structure exists whether there is a solar storm or not. It is a permanent feature of the planet's electrical architecture that textbooks have described for generations. What the Kyoto model proposes is that during periods of elevated solar activity, when charged particles and enhanced radiation flood the upper atmosphere, the total electron content of the ionosphere increases significantly. TEC is a measure of how many free electrons are packed into a column of ionosphere above a given point on the surface, and it is measured continuously by networks of GPS receivers that track the slight delay solar radiation introduces into satellite signals as it passes through the ionosphere. During geomagnetic storms, TEC spikes in ways that are well documented and routinely monitored. More electrons in the ionosphere means higher charge density in the upper plate of that natural capacitor, and when the charge density on one plate of a capacitor changes, the electric field between the plates changes proportionally. But here is where the model gets more specific and considerably more interesting. The Kyoto team did not just describe a simple top-down electric field strengthening uniformly between the ionosphere and the ground. They described a layered system with internal structure. The crust itself, particularly the fractured, fluid-saturated upper crust where shallow earthquakes occur, behaves like a stack of smaller capacitors nested inside the larger atmospheric one. Fractured rock contains nanometer-scale void spaces between mineral grains, along fracture surfaces, and within the crystalline structure of the rock itself. Those voids can contain supercritical water, which is water under conditions of such extreme temperature and pressure that it exists in a state between liquid and gas, exhibiting unusual electrical properties including very high dielectric constants that allow it to store and amplify electrical charge far more effectively than ordinary water. These microscale capacitors inside the rock can be charged and discharged by the field, propagating downward from the ionosphere. The result, if the model is correct, is that enhanced electrical fields from a geomagnetic storm do not simply stop at the surface or dissipate harmlessly into the shallow ground. They penetrate into the crust and concentrate in the exact zones where fractured, fluid-filled rock creates favourable conditions for charge amplification. The energy is transferred without physical contact between the ionosphere and the rock. No particles need to move from the ionosphere into the ground. The field does the work, the way a changing magnetic field induces a current in a wire without touching it, the way a magnet can move a metal object without making contact. And critically, this mechanism does not require enormous energy delivery to produce a physical effect on a fault zone. The fault zone does not need to be powered by the solar storm, the way a machine is powered by its fuel. It needs to be nudged. If a fault is already sitting at critical stress, the additional electrostatic pressure component, even measured in fractions of a megapascal, could be sufficient to trigger rupture that was going to happen anyway, just perhaps days or weeks later. The storm does not break the fault. It advances the timing of a break that was already coming, and that distinction between cause and trigger is the most important distinction in this entire story. Part 7. Pressure from space and why it's controversial. The Kyoto University estimate for the electrostatic pressure that could be generated inside critically stressed crustal zones by ionospheric enhancement during a significant geomagnetic storm comes out to several megapascals. Let's put that number in context because megapascals is not a unit most people encounter in daily conversation, and the context matters enormously for understanding why this estimate generated both attention and significant skepticism in equal measure. 1 megapascal is approximately 145 pounds per square inch. For reference, a standard car tyre runs at about 2 to 3 times atmospheric pressure, which translates to roughly 200 to 300 kilopascals, or 0.2 to 0.3 megapascals. Several megapascals means you're talking about hundreds of pounds per square inch of additional pressure potentially being applied to fault zones through this electrical coupling mechanism. That is not a trivial pressure. Applied to rock that is already near failure, even a fraction of that could matter. Now compare that to tidal forces, which are the most commonly cited example of an external influence on seismic activity, and which mainstream seismology already acknowledges with reasonable comfort. The gravitational pull of the Moon and Sun on the solid Earth, the the solid tide as opposed to the ocean tide, produces stress changes in crustal rocks in the range of roughly 0.001 to 0.01 megapascals. This is accepted science. Papers have been published showing that earthquake rates in some fault zones are modestly but measurably elevated during periods of higher tidal stress, particularly in regions with critically loaded faults. The effect is small. It does not override tectonic loading, but it is real and documented. The Kyoto model's estimates, if correct, suggest that solar-driven electrostatic forces during a significant geomagnetic storm could be somewhere between 100 and 1,000 times stronger than the tidal forces we already know affect seismic systems, 100 to 1,000 times stronger than tides. That number is why this paper generated attention. That is also precisely why it generated significant skepticism from researchers who study fault mechanics and earthquake physics, and the skepticism deserves to be taken as seriously as the excitement. The earthquake research community's reaction to the Kyoto findings has been measured and cautious, and the caution is scientifically legitimate rather than reflexively conservative. The mechanism proposed involves scaling from nanometer-scale electrical behavior in tiny rock voids up to fault zone scales spanning kilometers or tens of kilometers. That is a scaling leap of many orders of magnitude, and physics does not always behave predictably across that kind of scale jump. What works at the nanoscale in a laboratory sample of fractured granite does not automatically replicate when you try to apply the same mathematics to a fault zone that extends for 50 kilometers along strike and down through the entire brittle crust. The intermediate steps in that scaling argument require assumptions, and assumptions at each step can compound into significant errors by the end. There is also the question of competing explanations that always needs to be asked honestly. When you observe a temporal correlation between two phenomena, the most conservative scientific response is to ask whether the simpler explanation, pure coincidence, is sufficient before reaching for a causal mechanism. The frequency of geomagnetic storms during solar maximum and the frequency of significant earthquakes globally create a baseline probability of overlap that is not zero. Overlaps will happen. Some of those overlaps will look compelling. The challenge is distinguishing between overlaps that reflect a real physical connection and overlaps that are sampling accidents, and that distinction requires large data sets, rigorous statistical testing, and a physical mechanism that is consistent with established physics. The Kyoto model provides the physical mechanism part of that requirement more convincingly than anything that has come before it. Whether the magnitude estimates survive contact with detailed fault zone modelling is a question that will take years of follow-up research to fully answer. But the mechanism itself, electrostatic coupling through the global electric circuit, and the nested microcapacitor structure of fractured crust, is grounded in real physics. It is not the mechanism that is in question so much as the magnitude of the effect, and that is a much more tractable scientific problem than trying to defend a mechanism that has no physical basis at all. Part 8. The one-day lag nobody talks about. There is a piece of published research that does not get nearly the attention it deserves, and it connects directly to the timing of the Tonga-Samoa cluster on March 22nd, in a way that is difficult to dismiss once you see it laid out clearly against the timeline. In 2020, a study published in Nature Scientific Reports found a statistically significant correlation between solar proton density and the occurrence of magnitude 5 or greater earthquakes globally, with a lag time of approximately 24 hours between the solar measurement and the seismic response. Not simultaneous, not weeks later, not a vague window of several days that could mean almost anything. One day. A specific, measurable, reproducible delay that appeared consistently across the dataset when the researchers ran their analysis. That precision is not a minor detail. It is the detail that makes the findings scientifically interesting rather than merely suggestive. The implication of a lag is actually more scientifically interesting and more diagnostically useful than simultaneity would be, and it is worth slowing down on that point because it runs counter to how most people intuitively think about cause and effect. If earthquakes spiked at exactly the same moment as a solar storm peak, you could argue convincingly that the correlation was an artifact of the measurement process, or that both the storm and the earthquakes were responding to some third factor simultaneously, or that the apparent synchrony was sitting within the noise of the data rather than above it. Simultaneous correlations are actually easier to dismiss because they leave more room for alternative explanations that do not require a physical connection between the two phenomena. A one-day lag is different. A lag suggests a process that takes time to complete. Energy transfer, redistribution, propagation through a medium that responds with a delay built into its physical properties rather than instantaneously. That signature is more consistent with a genuine physical mechanism, specifically the kind of gradual electrostatic build-up and discharge that the Kyoto model describes, than with coincidence or measurement artifact. Coincidences tend to cluster around zero lag when you look at them statistically. Real physical mechanisms tend to produce characteristic delays that reflect how long the underlying process actually takes to move from input to output. Think about what the Kyoto mechanism actually involves at each step. A CME arrives and compresses the magnetosphere. The ionosphere responds to the changed electromagnetic environment over a period of hours as the storm develops. The total electron content increases as more charge accumulates in the upper atmosphere. The enhanced electric field between the ionosphere and the surface begins propagating downward into the crust. The microscale capacitor structures in fractured, fluid-saturated shallow rock begin responding to the change field conditions. Charge builds up, electrostatic pressure increases incrementally in the fracture network, and eventually, in a fault zone already sitting at critical stress, that accumulated additional pressure crosses the threshold and triggers rupture. Each step in that chain takes time. The whole sequence from CME impact to crustal stress change to fault failure, playing out over roughly 24 hours, is not just plausible given the mechanism, it is approximately what you would predict if you worked through the physics of how long each step takes. The 2020 study was not a one-off finding from a single research group working with a limited dataset and a methodology that has not been replicated or scrutinized. Subsequent analysis presented at the American Geophysical Union annual meeting in 2025 examined longer datasets spanning multiple solar cycles, going back decades in some cases, and found consistent correlation patterns between solar wind parameters and seismic event rates over multi-year periods. Multiple independent teams, using different subsets of the seismic catalogue, different solar wind parameters as their input variable, and different statistical methodologies for testing the correlation, all found variations of the same signal. The agreement across methodologically independent approaches is significant. In science, when different groups using different tools converge on the same answer, that convergence carries more weight than any single study regardless of how carefully that single study was conducted. The signal was not enormous. It is important to say that clearly and not bury it in the fine print. The correlation between solar wind conditions and earthquake rates is not so strong that it jumps out of the data immediately. It is not strong enough to use as a standalone forecasting tool in any reliable operational sense. You cannot look at today's solar wind data and predict tomorrow's earthquakes with the kind of precision that would be useful for evacuation planning or emergency response coordination. The effect, in the language of statistics, explains only a fraction of the variance in earthquake timing. The majority of that variance is still explained by tectonic loading rates, fault geometry, fault history, and the specific mechanical conditions of individual fault zones. Those factors dominate. The solar signal is a secondary influence riding on top of a much larger primary one. But here is why the correlation still matters enormously, even though it is not strong enough for prediction, and this distinction is worth spending a moment on because it is frequently confused in public discussions of earthquake science. The absence of a strong correlation would argue against any real physical connection. If you looked at solar wind data and earthquake rates across decades and found nothing, that absence of signal would be meaningful negative evidence. The presence of a weak but consistent correlation appearing across multiple independent datasets assembled by multiple independent research groups using multiple independent methodologies argues in favour of a real connection even if the effect size is modest. Weak signals that are reproducible carry more scientific weight than strong signals that appear only once. Science builds understanding through the accumulated weight of reproducible evidence, and the weight of evidence on the solar seismic correlation has been slowly but steadily accumulating for years, without any single landmark study that forces a paradigm shift. It has been building quietly in the background of the literature, while the main conversation in earthquake science focused elsewhere. There is another structural layer to this story that adds a repeating periodicity and makes the entire hypothesis testable in a very specific concrete way that does not require waiting for the next major geomagnetic storm. The Sun rotates on its own axis roughly every 27 days as seen from Earth, slightly slower at the equator than at the poles due to the Sun's fluid nature, a phenomenon called differential rotation that itself tells you something interesting about how the solar magnetic field becomes tangled and energized over time. Active regions on the solar surface, the areas associated with sunspot groups that produce more intense solar wind, more frequent coronal mass ejections, and more energetic particle radiation, rotate in and out of alignment with Earth on that 27-day cycle. When an active region faces Earth, conditions at our planet become more disturbed. When that same region rotates to the far side of the Sun, conditions quiet down. Then 27 days later, if the region survives, it rotates back into view and the disturbance returns. This creates a natural periodicity in the solar forcing reaching Earth that operates on a timescale of about 4 weeks. If solar activity genuinely influences seismic rates with a reproducible 24-hour lag, then you would expect to see mild periodicity in seismic data at roughly 27-day intervals. A subtle rhythm in earthquake occurrence rates that rises and falls in rough synchrony with the Sun's rotation, not a dramatic on-off pattern, but a gentle modulation sitting beneath the much larger variations driven by tectonic processes. Some researchers examining the global earthquake catalogue have claimed to find exactly this signal buried within the data, a 27-day periodicity in seismic rates that matches the solar rotation period, closely enough to be worth investigating seriously. The claim is disputed. It sits close to the noise floor of the available datasets, meaning that the signal, if it is real, is small enough that separating it from random statistical fluctuation requires long, clean datasets and careful analysis. Critics argue that the earthquake catalogue, despite being the most comprehensive record of global seismicity ever assembled, still may not be long enough or complete enough at the lower magnitude thresholds to distinguish a real 27-day periodicity from noise. The monitoring network has changed in sensitivity over the decades as new stations were added and instrumentation improved, which introduces non-uniform detection thresholds that can create artifacts in long-term statistical analyses. These are legitimate methodological concerns, not dismissive hand-waving. The researchers who dispute the 27-day signal are not arguing that the solar seismic connection is impossible. They are arguing that this particular dataset, analysed in this particular way, does not yet provide sufficient evidence to confirm it at the level of confidence the claim requires. That debate will not be resolved quickly. It will be resolved by more data, better instrumentation, longer catalogue records, and improved statistical methods for dealing with the non-uniformities in historical seismic catalogues. But the fact that the 27-day periodicity hypothesis is a testable prediction that can in principle be checked against growing datasets as seismic monitoring networks continue to expand their global coverage is the most important thing about it. A hypothesis that can be tested and potentially falsified is a scientific hypothesis. A pattern that keeps showing up in multiple independent datasets across multiple research groups using multiple methodologies, pointing consistently toward a connection between the Sun's behavior and the Earth's seismic response, is the kind of pattern that eventually stops being a curiosity and becomes a finding. The clock on that transition has been running for a while now, and the events of the last 72 hours just added another tick. Part 9. The feedback loop hypothesis. Everything discussed so far has pointed in one direction. The Sun affects Earth. Solar activity changes the ionosphere, and through the electrostatic coupling mechanism the Kyoto model describes, those changes may reach down into the crust and influence when faults that are already stressed decide to rupture. That is the direction researchers have been looking most intently, top down, from space toward the ground, solar input entering the system at the top of the atmosphere and propagating downward through a chain of physical processes until it reaches the brittle rock where earthquakes happen. But there is a second direction, and it flips the entire picture in a way that has significant implications for how we think about earthquake forecasting, planetary science, and the fundamental nature of the Earth as a system. Multiple independent research groups working with satellite data have now documented ionospheric anomalies that appear before major earthquakes. Not during the earthquake, not in the hours after, before, sometimes days before. The ionosphere above a future earthquake epicenter shows measurable changes in electron density, in radio wave propagation characteristics, in the very total electron content values that the Kyoto model uses as its primary input variable, appearing in the data days before the surface rupture actually occurs. The ground has not moved yet. No seismic waves have been generated. No fault has slipped. But the atmosphere above the future rupture zone is already behaving differently, already registering a departure from the background state that instruments in orbit can measure and record. This is a striking finding, and it demands explanation. The standard model of how earthquakes interact with the world above them assumes a largely one-way relationship. The ground shakes, and then things respond. Seismic waves travel outward through the crust. Buildings collapse or hold. Tsunamis form if the rupture is beneath the ocean. The atmosphere above is disturbed by the shaking itself, generating infrasound and atmospheric gravity waves that propagate upward. But all of that happens after the fact as a consequence of the rupture. What the satellite record appears to be showing instead is something that happens before the rupture, something that originates not in the violent release of stored elastic energy, but in the quiet, slow accumulation of stress in the days and weeks leading up to that release. The 2024 Noto earthquake in Japan, which struck the Noto Peninsula on January 1st of that year and caused widespread destruction and over 200 fatalities, was accompanied by pre-seismic ionospheric signals that researchers identified in retrospect in the satellite data. Going back through the total electron content records for the days preceding the rupture, anomalous values appeared above the epicentral region that stood out clearly from background variability. These were not subtle statistical artifacts at the margins of detection. They were measurable departures from the expected state of the ionosphere above that patch of Earth. The 2025 Myanmar earthquake sequence showed similar signatures in satellite TEC measurements prior to the main events, signals that, when examined after the fact, traced the outline of what was coming. The Cayman Islands earthquake activity in 2025 also generated ionospheric signatures that analysts flagged when they examined the pre-event data record. Each case, studied independently by separate research teams working with different datasets, pointed toward the same conclusion. Something happening deep in the crust was leaving a detectable trace in the atmosphere above it, and that trace was visible before the earthquake, not after. The proposed mechanism for these pre-seismic ionospheric signals works from the ground up rather than from the sky down, and it draws on well-established principles of rock physics and electrical geophysics. As stress builds in the crust in the days or weeks before a major rupture, the rock undergoes microfracturing, the opening of tiny cracks and grain boundaries that propagate through the crystalline structure of the crust as the stored elastic energy approaches the threshold for catastrophic failure. This microfracturing releases trapped gases, particularly radon, a radioactive noble gas that forms naturally from the decay of uranium and thorium in crustal rocks, and that, under normal conditions, remains locked within the mineral matrix. When microcracks open, radon escapes into groundwater and eventually into the atmosphere above the stressed region, where it can be detected by sensitive instruments at the surface. At the same time, the mechanical stress on the crystal lattices of quartz and other piezoelectric minerals in the crust generates electrical charges. This is the piezoelectric effect, a well-known physical phenomenon in which the deformation of certain crystal structures produces a separation of positive and negative charges across the crystal. Quartz, one of the most abundant minerals in continental crust, is strongly piezoelectric. As stress accumulates on a fault system and the surrounding rock deforms in response, countless tiny piezoelectric crystals throughout the stressed volume are generating tiny electrical charges. These charges accumulate, align, and find pathways to propagate upward through the conductive network of groundwater-saturated rock, through the lower atmosphere and eventually into the ionosphere, where they alter the local electron density in a way that satellite-mounted GPS receivers and radar instruments can detect as a change in total electron content. The stressed rock is, in this model, essentially broadcasting its internal state upward through the electrical structure of the planet, transmitting a signal that instruments in space can potentially detect before the rupture occurs. It is a form of planetary communication that operates entirely below the threshold of human perception, invisible to any sensor that is not specifically designed to look for it, but real and physical and grounded in mechanisms that have been studied and verified in laboratory settings. The piezoelectric effect is not hypothetical. Radon migration through rock is not hypothetical. The electrical conductivity of the crust and lower atmosphere is not hypothetical. What remains to be fully established is whether these mechanisms operate at the scale of real fault systems, producing signals large enough and consistent enough to be reliably distinguished from the background noise of a planet whose ionosphere is constantly being buffeted by solar wind, geomagnetic activity, weather systems, and the ordinary variability of tectonic stress. If both directions of this coupling are real, and the evidence for both is growing, even if neither is yet definitive, then the picture that emerges is not a one-way street from solar input to seismic output. It is a feedback loop. Stress building in the crust changes the electrical properties of the rock and the atmosphere above it. Those changes alter how much energy couples from the ionosphere back into the crust when a solar storm arrives. The altered crust, preconditioned by its own internal stress state, responds differently to solar forcing than an unstressed crust would. Earth and ionosphere maintain a continuous electrical conversation with each other, with the Sun contributing to that conversation from 93 million miles away, its contributions modulated by the internal state of the planet it is speaking to. This bidirectional framework has consequences that extend well beyond the question of earthquake triggering. It suggests that the ionosphere above a tectonically active region is not simply a passive receiver of solar input. It is also a kind of readout, imperfect, noisy, difficult to interpret but real, of the stress state of the crust below. A planet with active tectonics, with faults accumulating stress toward rupture, with stressed rocks leaking radon and generating piezoelectric charge distributions, is a planet whose upper atmosphere is subtly different from what it would be if the crust below were quiescent and unstressed. The ionosphere carries the fingerprint of geology. The implication of this bidirectional model is that Earth is not simply a passive geological object, slowly grinding through its tectonic cycles in isolation from the space environment surrounding it. Earth's internal stress state at any given moment is partly reflected in the electrical properties of the atmosphere above it. The planet is not inert, the crust is broadcasting, the ionosphere is listening, the Sun is occasionally shouting, and the message that travels between them moves in both directions simultaneously, a conversation rather than a monologue, a system rather than a chain of causes and effects. We're only now beginning to understand this, equipped for the first time with the right combination of tools. Global GPS networks now provide continuous total electron content measurements at resolutions and coverage that were unimaginable 2 decades ago. Satellite constellations monitor the ionosphere from above with increasing precision. Theoretical frameworks like the Kyoto model provide the physical grounding to interpret what the data is showing, connecting the dots between solar activity, ionospheric state, and crustal response in a way that is mathematically rigorous rather than merely correlational. Ground-based radon monitors, magnetometers, and electromagnetic sensors add additional dimensions to the observational picture. What remains is the work of turning this emerging framework into something reliable enough to be operationally useful. Pre-seismic ionospheric signals, even if real, are not yet a basis for earthquake warnings. The background variability is large, the signals are subtle, the mechanisms are incompletely understood, false positives would be damaging, and the statistical record of confirmed cases, while growing, remains too small to characterize with the rigor that operational forecasting requires. But the direction is clear. The Earth, the atmosphere, and the Sun are not 3 separate systems operating in parallel. They are one system, coupled electrically across every layer from the deep crust to the outer reaches of the ionosphere, and the conversation between them contains information that science is only beginning to learn how to read. Part 10, where science ends and speculation begins. At this point in a story like this, certain theories tend to surface with remarkable predictability, pulled into the narrative by the gravitational field of anything that combines solar storms, earthquakes, and the suggestion of hidden mechanisms. They arrive not as questions but as assertions, not as curiosity but as conclusion, and they carry with them the particular energy of ideas that have been repeated so many times in so many corners of the internet that repetition itself has come to function as a form of evidence. They need to be addressed directly, rather than left floating in the background, where they can do more damage than open examination would allow. Acknowledging them is not the same as dignifying them. It is, in fact, the only way to be fair to the actual science, which is genuinely interesting enough that it does not need the distortions conspiracy theory introduces to be worth taking seriously. The HAARP facility in Alaska gets mentioned anytime there is unusual geomagnetic activity combined with seismic events. It arrives in comment sections and forums and social media threads with the regularity of a geological formation, immovable and apparently immune to erosion by evidence. The pattern is consistent enough to be almost mechanical. A significant earthquake occurs, a solar storm has recently passed, and within hours the HAARP acronym appears, trailing its familiar cloud of insinuation. The facility becomes a kind of explanatory placeholder, filling the space where understanding has not yet arrived with the satisfying but false certainty of a named culprit. The High-Frequency Active Auroral Research Program is a real installation that conducts real ionospheric research using high-frequency radio waves to study the properties of the upper atmosphere. It is operated by the University of Alaska Fairbanks and has produced genuinely useful science about ionospheric physics, research that, in some cases, overlaps meaningfully with the kinds of topics discussed in this video. Ionospheric heating experiments, wave propagation studies, electron density measurements. These are legitimate areas of inquiry, and HAARP has contributed to them. The people who work there are scientists doing science, publishing in peer-reviewed journals, attending conferences, and arguing about methodology the way scientists do. None of that is secret. The facility's research program is publicly documented. HAARP is also genuinely not capable of producing the kind of effects being discussed here, and the reason for that is not a matter of opinion, of institutional credibility, or of who you choose to trust. It is a matter of basic physics, and the numbers are not close enough to make the question interesting. The total power output of HAARP at its maximum operational capacity is approximately 3.6 megawatts. This is enough to run a small neighborhood. It is a meaningful amount of power for a research facility. It is, in the context of space weather, a rounding error so small it essentially does not exist. The energy delivered to the magnetosphere by a G3 solar storm, a moderate to strong event, not an exceptional one, is measured in the tens of thousands to millions of megawatts equivalent over the duration of the event. That comparison is not a slight exaggeration deployed for rhetorical effect. It is an accurate description of the actual ratio between these two things. HAARP is a candle, the sun is a star. Suggesting that HAARP caused or triggered the G3 geomagnetic storm of March 20th, or that it produced the ionospheric changes the Kyoto model describes, requires believing that a 3.6 megawatt radio transmitter located in a field in Alaska can rival the electromagnetic output of a coronal mass ejection from a thermonuclear furnace 800,000 kilometers across. That is not a gap in understanding that more research might close. It is not a question of classified technology that might bridge the difference. It is a difference of many orders of magnitude that no amount of conspiratorial creativity can paper over, because physics does not have a classified annex where the rules are different. The Kyoto University mechanism is, in this respect, worth emphasizing for what it is as well as what it shows. It is a natural process, driven by natural solar variability, operating through natural physical structures, the ionosphere, the global electric circuit, the conductive pathways of the crust and atmosphere that have existed for as long as the Earth has had a magnetic field and a sun to orbit. The model does not invoke artificial forcing of any kind. There is no room in it for a transmitter in Alaska. The causal chain it describes begins 93 million miles away and operates through mechanisms that predate the existence of our species by billions of years. There are also claims circulating in certain online spaces that governments already possess functional earthquake prediction technology based on ionospheric monitoring and are deliberately concealing it for strategic or economic reasons, to avoid disrupting real estate markets, to maintain control over disaster response, to preserve some advantage in the management of catastrophic risk. The honest answer here is more nuanced than a flat denial, and that nuance is part of why the claim keeps circulating. Ambiguity, in an information environment optimized for certainty, tends to be colonized by whichever confident narrative arrives first. The science of using ionospheric precursors for earthquake forecasting is real. It is actively researched by legitimate scientific institutions with significant resources and no particular interest in keeping their work secret. China has launched dedicated satellites, specifically the CSES series, the China Seismo-Electromagnetic Satellite Program, designed explicitly to monitor ionospheric electrical anomalies above seismically active regions. This is a stated, publicly documented national research priority for a country with enormous earthquake exposure and a long history of seismic catastrophe. Russia has conducted similar research. Japan, which has as much motivation as any nation on Earth to develop earthquake forecasting capability, has invested substantially in ionospheric monitoring and pre-seismic signal detection. The field is not a fringe pursuit practiced only by outsiders working against institutional resistance. It is an active area of inquiry in earthquake-prone nations, conducted by mainstream researchers, published in mainstream journals, presented at mainstream conferences. The concealment claim collapses when you look at what is actually known and who actually knows it. The researchers doing this work are publishing it. The satellites collecting the data are publicly announced. The conferences where the results are discussed are open. If there is a conspiracy of silence, it is a remarkably porous one, conducted entirely in the open, in multiple languages, across dozens of institutions in countries that are not otherwise notable for their cooperative information sharing arrangements. Whether this research has produced functional prediction technology is a genuinely separate question from whether the underlying signals are real, and conflating those two questions is the source of most of the confusion. The current state of the published literature suggests that pre-seismic ionospheric signals exist and are detectable in retrospect. That is, when you go back through the satellite data after an earthquake has occurred, you can often find anomalous TEC values in the days preceding the rupture that stand out from the background. That is scientifically significant. It suggests that something real is happening and that it is, at least in principle, detectable. But retrospective detection and prospective forecasting are not the same thing at all, and the distance between them is where the actual scientific challenge lives. For a signal to be useful as a warning, it must be detectable in advance, with sufficient lead time, reliably enough to generate a meaningful signal-to-noise ratio, and specifically enough to identify a location and magnitude range that could inform protective action, all without producing so many false alarms that the warning system loses credibility and stops being used. Those are demanding requirements. The ionospheric signals, even where they are real, do not yet meet them. The background variability of the ionosphere is large. Solar activity, weather systems, seasonal variation, and a dozen other factors all produce TEC fluctuations that can resemble pre-seismic anomalies. Distinguishing a genuine earthquake precursor from that noise in real time before the earthquake occurs at a false alarm rate that public warning systems could sustain is an unsolved problem. That is not the same as concealment. That is science that has not yet crossed the engineering threshold from laboratory observation to operational system. The gap between those two stages is often enormous, and it typically takes decades to bridge, not because the underlying science is wrong, but because the engineering of reliable systems from imperfect signals is genuinely hard. The history of weather forecasting is instructive here. The physical mechanisms governing atmospheric behavior were understood in broad outline well before weather prediction became practically useful. The transition from physical understanding to operational forecasting required decades of data accumulation, modelling refinement, observational infrastructure, and hard-won lessons about the limits of predictability. Earthquake forecasting, if it arrives, will almost certainly follow a similar trajectory. The United States Geological Survey's official position remains that no reliable method of earthquake prediction exists. That statement is technically accurate in a precise and important sense. The USGS does not endorse solar triggering models as confirmed causal mechanisms. The gap between what the published research frontier is beginning to show and what official hazard agencies have incorporated into their operational models is real, and it is a legitimate source of frustration for researchers working at that frontier. But the gap exists not because of institutional suppression or deliberate concealment or the protection of vested interests. It exists because the evidence has not yet reached the threshold that justifies updating operational frameworks that affect public safety communications, emergency resource allocation, and the enormous social and economic consequences of issuing earthquake warnings in densely populated areas. That threshold is appropriately high, and the fact that it has not yet been met is not a scandal. We now have a mechanism. We have an increasingly coherent physical picture of how solar activity, ionospheric state, and crustal stress might interact. We have satellite data showing signals that could be precursors. We do not yet have confirmation that is robust enough, and specific enough and reliable enough to act on. Those are very different things, and keeping them distinct is the minimum that intellectual honesty requires. Part 11. Solar Cycle. 25 is breaking expectations. Everything discussed so far exists within a larger context that makes the current moment particularly significant, not just as a one-week anomaly or a single striking coincidence of solar and seismic activity, but as potentially the opening chapter of a multi-year period of elevated solar seismic interaction, unlike anything the modern monitoring era has had the instruments to properly observe and document. That context is Solar Cycle 25, and it is not behaving the way the people whose job it is to predict these things said it would. The divergence between forecast and reality is large enough, and has persisted long enough, that it has become one of the more discussed topics in solar physics, not as an embarrassment to be explained away, but as a genuinely interesting scientific puzzle about why our models of the sun's own internal dynamics remain imprecise enough to miss a cycle of this magnitude by this margin. The sun operates on an approximately 11-year cycle of activity, swinging between periods of relative quiet called solar minimum and periods of heightened activity called solar maximum. At solar minimum, sunspot numbers are low, the solar magnetic field is relatively organized and stable, and the solar wind that constantly flows outward past Earth is comparatively steady and calm. Geomagnetic storms still occur at solar minimum, but they are less frequent, typically weaker, and less often driven by the most energetic events. Solar maximum is a different environment entirely. The sun's internal magnetic dynamo, which drives the cycle, reaches its most complex and unstable configuration. Sunspot numbers peak. The solar disk is populated with active regions, tangled, stressed concentrations of magnetic flux that serve as the launching pads for coronal mass ejections and solar flares. The frequency of energetic events increases dramatically, and so does the probability that one of those events will be directed toward Earth. We have been tracking these cycles with reliable instrumentation since the mid-19th century, when systematic sunspot observations began to accumulate into a coherent long-term record. With careful historical reconstruction, the record extends further still, back through earlier centuries of astronomical observation, through the Maunder minimum of the late 17th century, when sunspots nearly vanished for decades, through the Dalton minimum of the early 19th century. The modern instrumental record gives us roughly 15 to 16 well-characterized solar cycles, enough to calculate averages, identify strong and weak cycles, and develop statistical models of how future cycles might behave. Cycle 25 began around December 2019, at the trough of the previous solar minimum, succeeding the notably weak Cycle 24 that had preceded it. When NOAA and the International Panel of Solar Scientists convened to issue the official prediction for Solar Cycle 25 before it began, they anticipated a modest cycle. The formal forecast called for a solar maximum with a smooth sunspot number of around 115, placing it below the historical average for modern cycles and making it broadly comparable in strength to the relatively quiet Cycle 24 that had just ended. The reasoning behind that prediction was not unreasonable. There were indicators in the solar magnetic precursor data suggesting the cycle's seed field was weak. Cycle 24 had itself underperformed expectations. Some analysts saw a longer-term trend toward diminishing solar activity and were watching for signs of a grand minimum, a prolonged multi-cycle suppression like the Maunder event. The prediction of a below-average Cycle 25 was a defensible scientific position given what was known. It has been wrong in a significant and increasingly difficult-to-ignore way. Solar Cycle 25 began exceeding the predicted sunspot numbers consistently from approximately 2023 onward, accelerating through the middle years of the decade at a pace that left the official forecast behind. By 2025, the cycle was tracking well above not just the official prediction, but the historical average of all measured cycles in the modern era, the average that the forecast had itself fallen below. Some months recorded sunspot numbers approaching or exceeding nearly double the predicted peak value. The cycle has been described by solar physicists as one of the strongest seen in decades, a significant overperformance relative to predictions issued by the best-equipped solar science institutions in the world using the best available models. That is not a minor calibration error. That is the cycle running in a fundamentally different regime than anticipated. Understanding why is an active area of research. The solar dynamo that drives the cycle is a deeply complex magneto-hydrodynamic system operating across the full depth of the convection zone that makes up the outer third of the Sun's volume, sensitive to flows and field configurations that cannot be directly observed from Earth. Our ability to predict cycle amplitude in advance remains limited in ways that are humbling for a field that has been studying the phenomenon for more than a century. The failure of the Cycle 25 forecast is not a one-off failure. Long-range cycle predictions have a poor track record historically, but the magnitude of this particular miss has renewed interest in understanding what the prediction models are getting wrong and whether the underlying physics is more variable than current theory accommodates. The practical consequence of the overperformance is that the solar environment in which the events of late March 2026 are occurring is substantially more active than was anticipated when the cycle began. The peak of the cycle, solar maximum, was anticipated in the 2025 to 2026 timeframe, and by the indicators available at the time these events unfolded, that peak region had not yet fully passed. Solar maximum is not a single day, or even a single month with a clean before and after. It is a sustained period of elevated activity that can persist for 1 to 2 years, during which high activity is the baseline rather than the exception, and during which major events, X-class flares, fast coronal mass ejections, multi-day geomagnetic storm sequences can occur with a frequency that would be unusual at other phases of the cycle. The system remains primed, the solar disk remains active. The probability of any given week producing a significant geomagnetic event remains elevated compared to what it will be in 3 or 4 years, when the cycle has declined toward its next minimum. The mechanism by which this sustained elevation matters for Earth is straightforward if the solar seismic coupling hypothesis has any validity at all. More active regions rotating across the solar disk means more coronal mass ejections launched toward the inner solar system. More CMEs means more geomagnetic storms reaching Earth, more G3, G4 and potentially G5 events in the remaining active phase of the cycle than in the quieter years that preceded it, or will follow it. And if the electrostatic coupling mechanism that the Kyoto model describes is real, if geomagnetic storms genuinely do alter ionospheric electron density in ways that propagate downward through the global electric circuit to influence the stress state of critically loaded faults, then more geomagnetic storms means more triggering opportunities. More windows during which a fault that has been accumulating stress for decades sits at the threshold while an external electrical perturbation shifts the balance. More moments during which the question of whether a rupture happens today or in 6 months might have an answer that is partly determined by what the Sun is doing rather than purely by the local tectonic loading history. This is the argument for why the current moment is more than a curiosity. It is not simply that a solar storm and a series of significant earthquakes happen to coincide in the same week. It is that we are potentially at or near the most active sustained period of an already overperforming solar cycle, in an era when the monitoring infrastructure needed to test the solar seismic hypothesis is, for the first time, good enough to produce the data required for serious analysis. Global GPS networks providing continuous total electron content measurements, dedicated satellites monitoring ionospheric electrical anomalies above active fault systems, seismic catalogues with enough depth and coverage to calculate meaningful global statistics. The Kyoto model and frameworks like it, providing the physical scaffolding to connect the observations into a coherent causal narrative rather than leaving them as an uninterpreted collection of correlations. The elevated seismic background that has been observed in parts of the global earthquake catalogue over the past 2 years may not be independent of the elevated solar activity over the same period. That connection has not been formally established. Making it would require careful statistical work to separate genuine signal from the noise of natural seismic variability, to control for the selection effects that make humans notice earthquake clusters when they are looking for them and miss them when they are not, and to demonstrate that the correlation holds across multiple cycle phases and multiple regions, rather than being an artifact of a particular dataset or a particular moment. That is achievable work, not impossible work. And if solar cycle 25 continues to run hot into its declining phase, if the activity remains elevated through the second half of the decade before eventually declining toward the next minimum, the dataset available for that analysis is going to grow considerably larger before the question can be considered settled. The Sun, in other words, is not done. The cycle has not closed. and the conversation between the star, the ionosphere, and the crust of this planet, a conversation that existed long before anyone was listening for it, continues in a period of unusual solar eloquence, with more instruments pointed at it than at any previous moment in human history. Part 12. The Equinox Effect, Hidden Amplifier. There is one more layer to the March 20th through 22nd timing that almost seems too neat to be real, which is exactly why it demands careful examination rather than either enthusiastic embrace or reflexive dismissal. Coincidences that feel engineered have a way of attracting the wrong kind of attention, the kind that skips the mechanism and goes straight to the meaning. But this particular coincidence is not a coincidence in the way that word is usually understood, because one of the two things that aligned on March 20th was not random at all. It was, in fact, one of the most predictable events in the astronomical calendar. March 20th was the spring equinox in the Northern Hemisphere, and the significance of that is not astrological or symbolic. It is physical, geometric, and thoroughly documented in the peer-reviewed literature of space weather science. There is a well-established, physically understood phenomenon called the Russell-McPherron effect that makes Earth significantly more vulnerable to geomagnetic storm impacts, specifically at the equinoxes, twice each year, in March and September, with a predictability and consistency that space weather forecasters already account for in their operational models. This is not fringe science. It is not a newly proposed mechanism awaiting validation. It was described by researchers C.T. Russell and R.L. McPherron in 1973 in a paper that has accumulated hundreds of citations and whose core predictions have been validated by more than 5 decades of subsequent magnetospheric observation. The effect is real, it is well characterized, and it is built into how professional space weather agencies think about storm risk across the calendar year. Understanding why it exists requires a brief excursion into geometry, specifically the geometry of Earth's magnetic field relative to the magnetic field carried by the solar wind as the planet moves through different positions in its annual orbit. Earth's magnetic field is approximately a dipole, like a bar magnet, with its axis tilted about 11 degrees relative to the planet's geographic rotation axis. That rotation axis is itself tilted about 23.5 degrees relative to the ecliptic plane, which is the plane of Earth's orbit around the Sun. The solar wind carries with it a magnetic field, the interplanetary magnetic field, or IMF, that has its own orientation, which varies continuously as different regions of the Sun rotate into view and as different solar structures pass by Earth. The critical variable governing how efficiently the solar wind transfers energy into Earth's magnetosphere is the orientation of the IMF's north-south component, called BZ. When BZ points southward, it is oriented opposite to Earth's own magnetic field at the dayside magnetopause, the boundary where the solar wind meets the magnetosphere. Opposite magnetic fields undergo a process called magnetic reconnection, where field lines break and reconnect across the boundary, opening a channel for solar wind energy to pour into the magnetosphere. The more strongly and persistently southward BZ points, the more energy enters, and the stronger the geomagnetic storm that results. When BZ points northward, the fields are aligned rather than opposed, reconnection is suppressed, and the magnetosphere remains relatively protected even under strong solar wind conditions. What the Russell-McPherron effect describes is how the geometry of Earth's orbital position at the equinoxes naturally enhances the southward projection of whatever IMF orientation the solar wind happens to be carrying. At the equinoxes, the combination of the Earth's axial tilt and the orientation of its magnetic dipole relative to the ecliptic creates a configuration in which the IMF is most efficiently projected into the southward orientation that drives reconnection. The same solar wind conditions, the same CME, the same magnetic field strength, the same BZ value in the reference frame of the solar wind will drive more intense geomagnetic activity when they arrive at the equinoxes than when they arrive at the solstices. The geometric amplification is not subtle. The same conditions that produce a G2 storm in June or December can produce a G3 storm in March or September. The storm that arrived on March 20th was therefore impacting Earth at the moment of peak annual geometric vulnerability, with the magnetosphere in the configuration that most efficiently converts solar wind energy into geomagnetic disturbance. In practical terms for the current story, this means the G3 storm of March 20th was not just a G3 storm in the abstract. It was a G3 storm delivered into the most favourable coupling geometry of the year, which means its effective geomagnetic impact, the actual energy deposited into the magnetosphere and ionosphere, the actual amplitude of the disturbances that propagated downward through the global electric circuit, was greater than the same nominal storm rating would imply at another time of year. The planet was more exposed. The coupling between solar wind and magnetosphere was more efficient. The ionospheric response to a given level of solar wind forcing was stronger. And all of this was predictable in advance, not with certainty about the storm's arrival, but with certainty about the enhanced vulnerability window that the equinox creates every single year. The historical data validates the equinox enhancement in ways that are by now thoroughly beyond dispute. Statistical analyses of geomagnetic storm intensity across the calendar year consistently show peaks centered around March and September, and relative troughs near the solstice months of June and December. This pattern appears in datasets spanning many decades and across multiple solar cycles of varying strength. It is not a marginal signal that emerges only with careful statistical coaxing. It is a robust, prominent feature of the Sun-Earth system that appears clearly whenever someone sorts geomagnetic storm records by calendar month and looks at the distribution. Space weather agencies know about it. Satellite operators know about it. Power grid managers in high-latitude regions know about it. It is part of the background knowledge of the field, the kind of thing that gets taught in graduate courses on magnetospheric physics without any particular emphasis because it is simply accepted as established. What has not been as extensively examined, and this is where the current story connects to something genuinely new rather than simply well known, is whether the equinox enhancement in geomagnetic coupling translates into a corresponding equinox enhancement in whatever solar seismic triggering mechanism the Kyoto model describes. The physical logic suggests it should. If the mechanism works by coupling solar wind energy through the ionosphere and down through the global electric circuit to influence stress states on critically loaded faults, then anything that increases the efficiency of the first step in that chain, the coupling between solar wind and magnetosphere, should amplify the downstream effects as well. A stronger ionospheric disturbance for a given level of solar input, a larger electrical perturbation propagating downward through the crust, a larger nudge applied to faults that are already sitting near their failure threshold. There is no obvious physical reason why this amplification would stop at the magnetosphere and not continue downward through the chain. And if it does continue, if the equinox enhancement in geomagnetic coupling has a corresponding equinox enhancement in seismic triggering probability, then the implication is significant. It means that the late March and late September windows are not merely periods of elevated space weather risk. They are periods of elevated seismic risk as well, specifically for faults that are already critically stressed, specifically during active phases of the solar cycle when the solar wind itself is more energetic and more frequently disturbed. The vulnerability is compounded. Stronger solar activity from an overperforming cycle, delivered into the most efficient coupling geometry of the year, applied to a planet whose most seismically active regions contain faults that have been accumulating stress for years or decades. This is a testable hypothesis, and the fact that it is testable using data that already exists is perhaps the most important point. The global seismic catalogue goes back more than a century in its modern instrumental form, and well-calibrated records of moderate to large earthquakes extend back far enough to encompass many solar cycles and hundreds of equinox windows. The geomagnetic record extends back equally far, with sufficient coverage to characterize storm activity by season and cycle phase. If there is a statistically meaningful excess of large earthquakes in the equinox months, particularly during the active phases of strong solar cycles, and particularly for shallow earthquakes on the kinds of strike-slip faults that the Kyoto model suggests would be most sensitive to the electrostatic triggering mechanism, that excess should be visible in the data. It would not be obvious to casual inspection, because the natural variability of the seismic catalogue is large, and the signal, if it exists, would be moderate in size and would require careful statistical controls to extract from the background. But it is not beyond reach. It is the kind of analysis that a well-equipped research team could undertake with existing tools and existing data. What March 20th through 22nd of 2026 provides, in this context, is not proof of anything. A single week of events, however striking in their timing and clustering, cannot establish a causal relationship that requires a statistical argument to demonstrate. What it provides is a vivid illustration of the mechanism at a moment when all the relevant factors converge simultaneously: an overperforming solar cycle near its maximum, a significant CME arriving at the exact moment of equinox geometric amplification, a series of major earthquakes distributed across the days that followed. The pieces fit the hypothesis. The next piece of the puzzle is already in the catalogue, distributed across decades of earthquake and geomagnetic records waiting to be examined with the right question in mind. The answer, whatever it turns out to be, is within reach. Someone just needs to look. Part 13, the March 26th, CME, a live experiment. There is another coronal mass ejection heading toward Earth. Current forecasts as of this script indicate a glancing blow arrival around March 26th, producing expected geomagnetic conditions in the G1 to G2 range, possibly edging higher depending on the precise magnetic field orientation embedded within the CME when it arrives at the magnetopause. That uncertainty is not a failure of the forecasting system. It is an honest reflection of a fundamental physical limitation that no amount of additional computing power or modelling sophistication has yet overcome. Solar wind forecasting at the 72-hour range carries real uncertainties under the best conditions, and the most critical variable, the north-south orientation of the interplanetary magnetic field's BZ component, which determines how efficiently the CME's energy couples into Earth's magnetosphere, cannot be measured directly until the CME reaches the L1 Lagrange point, the gravitational balance point between Earth and Sun where the monitoring spacecraft DSCO-VR and ACE are stationed. That measurement arrives approximately 15 to 60 minutes before impact, depending on the CME's speed. By the time you know what BZ is doing, the storm has already begun. The storm will likely be weaker than the G3 of March 20th, but it is arriving, and its arrival matters for reasons that go beyond the routine tracking notation that space weather agencies will attach to it in their daily bulletins. What this CME represents, in the context of everything discussed above, is something more specific than another entry in the space weather log. It is a test. Not a controlled laboratory experiment. The Earth does not cooperate with controlled conditions. The Sun does not hold variables constant while one parameter is adjusted, and the global fault system does not pause its tectonic loading schedule to serve as a clean experimental substrate. None of the conditions that make laboratory science tractable are available here. But science has always had a second mode of operation for precisely these situations, deployed whenever the phenomenon of interest operates at scales or timescales that put it beyond direct experimental manipulation. That mode is the natural experiment, a situation where nature itself creates conditions that approximate the structure of a test, where one variable changes while others remain approximately constant, and where observation of the outcome can meaningfully distinguish between competing hypotheses. The March 26th CME arrival is a natural experiment in this sense. The solar forcing conditions are similar in kind to those of March 20th, a CME-driven geomagnetic disturbance, the same physical mechanism, the same chain of processes from solar wind interaction to magnetospheric compression to ionospheric disturbance to potential downward coupling through the global electric circuit. The intensity is expected to be lower, which is itself informative. If the solar seismic correlation has any dose-response character, a weaker storm should produce a weaker signal in the seismic data, and a pattern that shows up at G3 but not at G1 or G2 would tell us something meaningful about thresholds and proportionality. The equinox geometric amplification is no longer at its annual peak, since several days have passed since the exact equinox alignment, but the Russell-McFerran enhancement fades gradually, rather than switching off instantly, so some residual amplification likely remains. The conditions are similar enough to be comparable and different enough to be informative. If the solar seismic mechanism proposed by the Kyoto model is real, if the lag correlations that appear in the published research reflect an actual physical process operating through the electrostatic coupling pathway rather than a statistical artifact generated by cherry-picked data and post-hoc pattern recognition, then the 48 to 72 hours following the March 26th CME impact become a data window of genuine scientific interest. The hypothesis makes a specific prediction: elevated seismic probability in already stressed shallow fault regions during that window, concentrated in the types of faults, particularly strike-slip systems at shallow crustal depths, that the Kyoto model identifies as most sensitive to the proposed triggering mechanism. If major seismic activity occurs in that window, it is consistent with the hypothesis. If the window passes quietly, with global seismic activity tracking at or below background rates, that is evidence against the hypothesis, not conclusive refutation from a single case, but evidence that accumulates weight alongside other quiet windows and must eventually be accounted for by anyone arguing for the correlation. This is not a prediction that an earthquake will definitely occur. That framing would be scientifically indefensible and practically harmful, because it implies a certainty that does not exist, and a specificity of location, magnitude, and timing that the mechanism, even if real, does not yet provide. The honest and scientifically defensible framing is probabilistic. If the mechanism is real, the conditional probability of significant seismic activity on critically stressed shallow faults is elevated during the post-storm window relative to baseline. Elevated, not certain. Conditional on a mechanism that has not yet been formally confirmed. Stated as a testable expectation about a distribution of outcomes, not as a prophecy about a specific event. What makes this moment unusual is that observation of this natural experiment is not restricted to the researchers who study the phenomenon professionally, working with datasets that will be analysed and published months or years after the events in question. The data streams are public and they are live. The USGS earthquake feeds update continuously, with new events appearing in the catalogue within minutes of detection by the global seismic network, their magnitudes and depths and epicentral coordinates available to anyone with a browser pointed at the right URL. The NOAA space weather indices, the KP index tracking global geomagnetic activity, the DST index measuring the ring current injection that serves as a proxy for storm intensity, the real-time solar wind data from L1, update every few minutes, publicly, without subscription or credentials. The total electron content maps that the Kyoto model uses as its input variable are generated and published in near real time by multiple institutions. Anyone with enough curiosity and enough patience can watch all of these streams simultaneously, tracking the geomagnetic disturbance as it develops, and then watching the seismic catalogue in the hours that follow. This democratization of real-time scientific observation is itself historically unusual. The lag correlation between solar storms and earthquake occurrence that researchers have been studying for decades was, until recently, something that could only be examined retrospectively by scientists with access to archived datasets and the analytical tools to process them. The events happened, the data was collected, months passed, papers were written. The public learned about the research, if at all, through press releases and science journalism that arrived long after the fact. What exists now is something different, a situation where the hypothesis is on the table, the mechanism is publicly explained, the predicted lag window is specified, and the relevant data is streaming in real time on public servers. The observation is no longer the exclusive province of specialists. It is happening in the open, available to anyone motivated to look. This is how science works at the frontier, and it is worth being explicit about what that means. It does not mean that majority opinion among non-specialists constitutes evidence. It does not mean that pattern recognition by motivated observers browsing earthquake maps constitutes confirmation. Individual human beings are spectacularly bad at the kind of rigorous statistical reasoning needed to distinguish genuine signal from the noise of a naturally variable seismic catalogue, and motivated observers are worse still because they are watching for a pattern they expect to find, and will find it in the noise whether it is there or not. What the public observability of real-time data provides is something different and more modest, a form of collective attention that keeps the question alive, that generates a community of informed observers who will notice if the pattern appears again, and that creates social and scientific pressure for the formal analysis that can actually answer the question rigorously. Science at the frontier advances one event at a time, one case study at a time, building toward the statistical threshold where a pattern becomes too consistent across too many independent observations to be attributed to chance. A single event proves nothing, and every statistics textbook written in the last 100 years will remind you of this with some variation of the phrase. 2 events with the same structure are a hint worth recording. 5 events consistently matching the predicted lag window across multiple solar storm intensities and multiple geographic regions starts to look like a signal that demands explanation, and formal investigation. 10 consistent events, properly documented and analysed with appropriate controls, is the kind of result that lands on the desk of a funding agency and generates a serious study proposal, a dedicated research programme, and eventually the kind of large-scale confirmatory analysis that either establishes or refutes the mechanism beyond reasonable scientific doubt. The March 26th arrival is one more data point in a series that is still actively being written, in real time, on actual instruments distributed across actual fault zones, on a planet orbiting an actual star that is currently running substantially hotter than anyone predicted when the current cycle began. The events of late March 2026 will eventually take their place in a dataset that someone somewhere will analyse carefully. The outcome of that analysis is not yet known, because the data is still arriving, the sun is not done, the catalogue is still open, and the question that connects all of this, whether the star at the centre of our solar system plays a role in determining when the ground beneath our feet decides to move, is still, genuinely, unanswered. Watch the data. Not because the pattern guarantees anything, because science runs on observation, and right now, there is something genuinely worth observing in real time. Part 14. Earth isn't the only planet reacting. The same sun that fired the coronal mass ejection that struck Earth on March 20th sends its solar wind and energetic radiation across the entire heliosphere, reaching every planet, moon, asteroid and comet from Mercury out to the termination shock at the boundary, where the sun's influence gives way to interstellar space. Earth is not unique in having a response to solar variability. It is simply the planet we have been monitoring most carefully and for the longest time, with the densest network of instruments, the deepest historical records, and the greatest personal stake in the outcomes. That creates a selection bias, a deeply understandable one, but a bias nonetheless, in how we think about solar-planetary interactions. We see the Sun-Earth relationship most clearly because we have looked at it most intently. But if the connection between solar activity and geological behaviour is real at Earth, the right scientific question is not whether that connection is somehow special to our planet. It is whether the same connection operates wherever the physical conditions allow it, across the solar system, on bodies with different magnetic fields, different atmospheres, different interior structures, and different relationships to the solar wind. The answer, when you look at the broader picture, is that electromagnetic coupling between the Sun and planetary bodies is not an exotic hypothesis confined to the edge cases of Earth science. It is a pervasive feature of the solar system, operating at different scales and through different mechanisms on every body large enough to have a geological interior and an atmosphere. Earth may be the place where we have characterized it most thoroughly, but it is far from the only place where it is operating. Mars presents the most immediately interesting comparison case, partly because of its similarities to Earth, and partly because of its profound differences. Mars is a terrestrial planet with a rocky crust, a differentiated interior, a thin atmosphere, and a surface geology shaped by billions of years of volcanic activity, impact cratering, and tectonic stress, even in the absence of the active plate tectonics that dominates Earth's surface evolution. But Mars has a thin, patchy magnetosphere, the remnant of what was once a stronger global dipole field that the planet lost roughly 4 billion years ago when its internal dynamo shut down. The leading explanation for that shutdown is that Mars's smaller size caused its core to cool faster than Earth's, eventually dropping below the temperature threshold needed to sustain the convective circulation of molten iron that generates a planetary magnetic field. The result is a planet that retains localized crustal magnetic anomalies, frozen in remnants of the ancient field, preserved in certain highland regions, but lacks the global magnetospheric shield that protects Earth from direct solar wind bombardment. Without that shield, Mars is exposed to the solar wind in a way Earth largely is not. During significant solar storms, the Martian ionosphere experiences measurable perturbations that have been documented in remarkable detail by NASA's MAVEN mission, which has been orbiting Mars since 2014 specifically to study the upper atmosphere and its interaction with the solar wind. MAVEN has measured the rates at which the solar wind strips ionospheric material directly from the Martian upper atmosphere, and those rates increase substantially during active solar periods and CME impacts. During major storms, the structure of the Martian ionosphere changes dramatically, with electron density profiles shifting in ways that would have significant implications for any crustal electrical coupling process, analogous to what the Kyoto model describes at Earth. The global electric circuit at Mars, to the extent one exists in its attenuated atmosphere, is far more directly and violently perturbed by solar activity than Earth's, precisely because there is no magnetosphere mediating the interaction. Mars does not have plate tectonics in the sense that Earth does, having lost the internal heat necessary to drive crustal recycling and the large-scale surface renewal that comes with it. But it does have Marsquakes, and this is where the picture becomes considerably more interesting than the conventional view of Mars as a geologically dead world would suggest. NASA's InSight lander, which operated on the Martian surface from November 2018 until its solar panels were finally overwhelmed by dust accumulation in December 2022, carried a seismometer sensitive enough to detect Marsquakes, and it did so in abundance. InSight recorded hundreds of seismic events during its operational period, ranging from small microseisms at the limits of detection to events large enough to be unambiguously identified as genuine quakes, with source mechanisms broadly analogous to intraplate seismicity on Earth. Some of these events showed waveform characteristics suggesting sources in the deeper crust or upper mantle, implying that Mars retains a seismically active interior despite the absence of plate tectonics. The Martian crust is stressed, probably by residual thermal contraction, as the planet continues its long, slow cooling, and that stress releases periodically in seismic events. Whether Martian seismic activity shows any temporal correlation with solar storm activity has not yet been studied with the statistical rigour that Earth's much longer and denser catalogue would allow. The InSight dataset is short, roughly 3.5 years, and the events it recorded were mostly small, making the statistical population available for correlation analysis limited. But the question is now considerably more interesting than it was before the Kyoto model provided a physical framework for thinking about how solar activity might couple into crustal stress, and before InSight demonstrated that Mars has a seismically active interior worth asking the question about. Future Mars seismology missions, if they are designed with this hypothesis in mind and equipped with the solar wind monitoring capability needed to characterize the electromagnetic environment simultaneously with the seismic record, could provide a genuinely independent test of whether solar seismic coupling is specific to Earth or operates more broadly on rocky planets. Jupiter's situation is different again, and it illustrates something even more fundamental: that electromagnetic coupling between a star and a planet's geological or volcanic behaviour is not a theoretical possibility awaiting its first confirmation. It is an observed, measured, currently operating system, visible through any telescope large enough to resolve Jupiter's disk and its innermost large moon. Jupiter's magnetosphere is the largest coherent structure in the solar system that is not the Sun itself. It extends hundreds of millions of kilometres into space, far enough that if it were visible to the naked eye from Earth it would appear larger in the sky than the full moon. Within this enormous magnetic structure, Jupiter's solar wind interaction produces dynamic responses to variations in solar activity, compressions and expansions of the magnetospheric boundary, intensifications of radiation belts, changes in the auroral systems at Jupiter's poles that have been observed and modelled in detail by spacecraft from Pioneer and Voyager through Galileo and most recently Juno, which has been orbiting Jupiter since 2016 and returning detailed measurements of the Jovian magnetic environment. Io, Jupiter's innermost large Galilean moon, is the most volcanically active body in the solar system. Its surface is continuously reshaped by eruptions that dwarf anything in Earth's volcanic record, with lava lakes, plume eruptions reaching hundreds of kilometres above the surface, and sulfur dioxide frost deposits that cover and recover the terrain on timescales of years. This extraordinary volcanic activity is driven primarily by tidal heating, the continuous flexing of Io's interior by the competing gravitational pulls of Jupiter, Europa and Ganymede, which maintain Io in a slightly eccentric orbit and pump enormous amounts of mechanical energy into its interior. But Io's volcanism is also significantly influenced by the electromagnetic interaction between the Moon and Jupiter's magnetosphere, and this is where the analogy to Earth becomes most directly relevant. Io orbits deep within Jupiter's magnetic field, moving through field lines at a velocity that makes it act as an electrical generator in the same way a conductor moving through a magnetic field generates a current. The currents produced by Io's motion flow along magnetic field lines between the Moon and Jupiter's upper atmosphere, producing the Io flux tube, a tube of electrical current connecting Io to Jupiter that has been directly measured by spacecraft and whose footprint in Jupiter's atmosphere produces a distinct auroral spot that has been imaged from Earth. This electromagnetic connection between Io and Jupiter contributes to the intense internal heating that drives Io's volcanism, adding to the tidal component and producing a combined output that makes the Moon a continuously erupting geological machine. That is not an analogy or a hypothesis. It is a documented, quantitatively characterized physical system operating in our solar system right now. Electromagnetic coupling between a body's magnetic environment and another body's geological activity has been directly observed, measured, and modelled at Jupiter Io. The principle that exterior electromagnetic forcing can influence interior geological behaviour has been established observationally, not just theoretically, at a scale that leaves little room for doubt about the basic physical possibility. The larger perspective this establishes is important for understanding why the Kyoto model deserves serious consideration rather than reflexive dismissal as physically implausible. Earth is not a sealed geological system operating in isolation from the space environment that surrounds it. No planet is. The Sun is the central engine of an electromagnetic system that pervades the entire heliosphere, and every body within that system responds to its variations in ways that depend on local properties: the body's magnetic field strength and geometry, its atmospheric density and conductivity, its internal heat budget, its surface geology, the state of stress in its crust. Earth's seismic behaviour may be one expression of a planet-wide electrical responsiveness to solar forcing that we have only recently developed instruments sensitive enough to begin quantifying, a phenomenon that is neither exotic nor implausible, but simply one more manifestation of the fact that we live not in isolation from the cosmos, but embedded within it, subject to its variations, shaped by its rhythms, and connected through fields and particles and waves to a star that has been driving the behaviour of this entire system for 4.5 billion years. Part 15. The unanswered question that changes everything. Come back to where this started. 3 different tectonic systems, 4 days, multiple magnitude 6+ earthquakes distributed across nearly opposite sides of the planet, a G3 geomagnetic storm running simultaneously, a paper from Kyoto University published weeks earlier proposing the first complete physical mechanism connecting solar activity to crustal stress, multiple peer-reviewed studies pointing toward a consistent 24-hour lag correlation between solar wind parameters and global seismic event rates, the Russell-McFerran equinox amplifier operating at maximum geometric efficiency on the exact day the storm arrived, solar cycle 25 running significantly hotter than anyone predicted, potentially sustaining elevated triggering opportunities for months or years to come. Each of those pieces, taken individually and in isolation from the others, is explicable without invoking anything outside the standard framework. Earthquakes happen. They happen every day, in multiple locations, at a range of magnitudes, because the planet's tectonic system never stops loading stress onto fault systems that will eventually release it. Geomagnetic storms happen during solar maximum with increased frequency, because that is what solar maximum means. Papers get published proposing mechanisms that may or may not survive the years of scrutiny, replication attempts, and critical re-examination that constitute the peer review process in its extended form. Correlations appear in datasets and sometimes dissolve when examined more carefully, when the statistical controls are tightened, when the selection criteria are questioned, when a longer baseline of data dilutes what looked like a robust signal into background noise. None of the individual pieces in this story is by itself extraordinary. Every one of them has a mundane explanation that requires no new physics and no revision of established frameworks. What is harder to dismiss, what becomes increasingly difficult to wave away as the pieces accumulate, is the way these specific pieces assemble into a coherent structure that points consistently in the same direction. Not proof. Not a closed case that forecloses all other interpretations and demands immediate revision of every seismic hazard model ever constructed. A coherent structure, which is a different and more modest thing, but still a significant one. Multiple independent lines of evidence, statistical studies conducted by different research groups with different methodologies and different data sets, physical mechanism proposals grounded in established electromagnetic physics, historical correlation analyses spanning decades of solar and seismic records, real-time event timing that matches the predicted lag window, with uncomfortable precision, all pointing toward the same underlying relationship. When independent lines of evidence converge, science pays attention. That convergence is not the conclusion. It is the signal that the conclusion is worth pursuing. The mechanism the Kyoto model describes would predict exactly the kind of shallow strike-slip fault activation that characterized the March cluster. It would predict near global distribution of triggered events, rather than a single regional cluster with a clear local initiating cause, because the ionospheric disturbance during a major geomagnetic storm is planetary in scale, not local. It would predict the specific lag that placed the largest events in the 48 to 72 hour window after the storm's peak, matching the propagation time for the electrostatic perturbation to work its way downward through the global electric circuit to fault depths. It would be amplified by equinox geometry, and it was amplified by equinox geometry on the exact day the storm arrived. If you had written those predictions down at the beginning of the week, before the storm peaked, before the earthquakes occurred, before the timing became apparent, and then watched what unfolded over the following 4 days, you would be having a very uncomfortable conversation with yourself about whether coincidence is a sufficient explanation for what you are seeing. The fundamental question in seismology has always been what determines when a fault breaks, not why, because the why is well understood in broad outline and has been for generations. Plates move because the mantle convects, driven by the residual heat of planetary formation and the ongoing heat of radioactive decay in the deep interior. Moving plates carry crustal blocks with them, grinding them against each other at boundaries, building elastic strain in the rocks on both sides of locked fault surfaces over decades and centuries. Eventually, the accumulated stress exceeds the frictional strength, holding the fault locked. The fault slips, elastic energy is released as seismic waves, and the surrounding rocks relax into a new configuration until the cycle begins again. That chain of causation is established geology. It is not in dispute, and nothing discussed in this story challenges it. The when has always been more elusive, and the elusiveness has not been for lack of effort or intelligence applied to the problem. Faults that appear to be at critical stress based on accumulated strain measurements and historical rupture histories do not always rupture on schedule. Regions expected by every available model to be quiet sometimes activate with major events that arrive without obvious immediate precursors. Regions expected to be seismically active on the basis of their tectonic setting, and stress accumulation rates sometimes stay locked for decades longer than the models predict, storing energy that will eventually be released in a larger event than a more regular release schedule would have produced. The timing of earthquake rupture has resisted prediction with a stubbornness that has outlasted generations of researchers and consumed enormous investments in monitoring infrastructure, physical modelling, computational approaches, and statistical analysis. All of that investment has produced genuine advances in understanding, better characterization of fault systems, better probabilistic hazard estimates over long-time windows, better real-time monitoring of seismic sequences as they evolve. What it has not produced is reliable short-term forecasting, the ability to say with meaningful confidence that a damaging earthquake will occur in a specific region within a specific time window short enough to be operationally useful. The possibility that the Kyoto model raises, and that the accumulated correlation studies increasingly support as more than a speculative possibility, is that the Sun has been quietly participating in that timing question for as long as the Sun has existed, and the Earth has had an ionosphere and a global electric circuit connecting them, not overriding tectonics, not manufacturing earthquakes from geological silence in regions where no stress has accumulated and no fault has been loaded toward failure. The solar contribution, if it is real, is not a replacement for tectonic causation, but a modulation of it, an external influence that operates on fault systems that are already approaching their failure threshold, adding or subtracting a small electrostatic component to the stress state that pushes some faults over threshold days or weeks earlier than they would have crossed it through tectonic loading alone, and perhaps leaving others locked slightly longer during extended periods of solar quiet, allowing stress to accumulate to a level that produces a larger eventual rupture. The Sun, in this picture, does not decide which faults break. Tectonics decides that. The Sun may influence when. If that is true, and it remains an if, a well-motivated and increasingly supported if, but an if nonetheless, then every seismic hazard model ever constructed has been operating with a missing variable. not a small second-order correction at the margins of the calculation, the kind of refinement that improves a model's accuracy by a few percent without changing its fundamental structure. A variable with a known 11-year periodicity, a known 6-month seasonal amplification driven by orbital geometry, and a physical mechanism that is now, for the first time, described in enough detail to make quantitative predictions. A variable that is, in principle, more predictable at long range than any internal tectonic process because the Sun's behavior is observable continuously across the entire planet simultaneously. Its activity can be forecast with some reliability days in advance. Its cycle phase is known months and years ahead, and the geometric amplifications produced by the Russell-McFerran effect at the equinoxes are predictable essentially indefinitely into the future. The solar component, if real, is the most foreseeable part of a system that has so far resisted forecasting almost completely. We have been asking what breaks the fault. We have been examining the geology meticulously and productively, the fault geometry and orientation, the accumulated strain measured by GPS networks and geodetic surveys, the fluid pressure in the pore spaces of the surrounding rock, the history of previous ruptures and the recurrence intervals they imply, the static and dynamic stress changes transferred from nearby events. All of that work is necessary and none of it is wrong. It has produced real knowledge and genuine improvements in how we think about seismic hazard. But we should also have been asking what is happening 93 million miles away on the days before a fault breaks. We should have been keeping one eye on the seismometer and one eye on the Sun, maintaining both data streams simultaneously, looking for the relationship between them with the same rigor and the same resources we have applied to understanding the purely internal dynamics of the fault system. The Sun has been sending signals across the heliosphere for 4.5 billion years. The Earth has been responding, its magnetosphere deflecting and channeling the solar wind, its ionosphere absorbing and redistributing the energy that gets through, its global electric circuit transmitting that energy downward through the atmosphere to the surface and into the crust. The ionosphere has been the medium through which part of this conversation between star and planet has been conducted, continuously, since before the first living thing drew energy from a chemical gradient in a warm ocean. We are only now, in this specific moment of accumulating research, improving instrumentation, and theoretical frameworks that finally connect the pieces into a coherent mechanism, beginning to understand that solar activity, ionospheric response, crustal stress, and earthquake timing are not 4 separate phenomena that happen to share a timeline. They are one system, one continuous conversation conducted across every scale, from the nuclear reactions in the solar core to the microscopic fracture of quartz crystals in a fault zone at 10 kilometers depth. We have been looking in the wrong place all along, and the right place has been burning 93 million miles away, visible to anyone who looked up, patient and constant and indifferent to whether we were paying attention, waiting to be understood.